Hello everyone. Today is day 27. Which day it is? Yes, today is day 26 of us solving 30 machine learning problems in 30 days. So, this is a challenge that we have started on September 9 or 10, I guess. So, yes, we are on day 26. So, the problem is that we have to do time series forecasting of electricity consumption using LSTM. This is going to be a deep learning problem. So let's start. And the flow is going to be same. I'm going to use ChatGPT to help me with the whole code and everything. And if I'll get stuck with any terminology that I do not understand, I'll ask ChatGPT. Or if I'll not get the answer, maybe I'll go and get the answer from Google. So this is a challenge that I'm doing to learn by doing. So yes, let's get started. Hey, it is day 26 and here is the problem title. Let me go and understand what this problem is about and why we are doing it. So we are doing it. This is going to be my first attempt at building the convolutional neural network using CIFAR 10, a major milestone in deep learning of image data. So it says that the problem is useful for predicting future electricity consumption based on historical data, as LSTMs are well suited for capturing temporal dependencies and in time series data. I'm going to say this is my first attempt. So can we go as basic as possible and not use advanced concepts of deep learning yet? Also, please be as descriptive as possible. Yes, it says that since this is your first attempt at building a deep learning model, we'll keep it very basic and focus on building a simple LSTM model for time series forecasting while keeping everything as clear and descriptive as possible. So let's. So yes, it says since this is your first attempt at building a deep learning model, we'll keep it very basic and focus on building a simple LSTM model for time series forecasting while keeping everything as clear and descriptive as possible. I'll walk you through each step carefully. Okay. So what is LSTM and why use it for time series forecasting? We did one problem on time series forecasting. We forecasted the weather actually, but the model was different, I guess. So here we are going to use LSTM, which is long short term memory. It is a type of recurrent neural network that is specifically designed to handle sequential data. Okay. So it is a model which is of what type? Recurrent neural network. We do not know what that is, and why do we use it? Because it is specifically designed. The importance of it usage actually is it is designed specifically to handle sequential data. Okay, it can remember patterns from the past and use them to predict future events, which makes it ideal for time series forecasting. Okay, that's something that I understand. So it uses the past event, remember the past event, and on the basis of that it predict the future events, and that is why it is very ideal for time series forecasting. For forecasting electricity consumption, we want the LSTM model to learn the patterns like daily or weekly fluctuations. Okay, so it is going to identify the patterns and use them to predict future values based on historical data. Okay, load the step by step we are going to load the data. The usual step, pre-process the data. That we are going to do, load the data. We will see how pre-process data, create and train the LSTM model, and evaluate the model and visualize the prediction. Okay. So it says if you have a data, we need to load that. We'll see what the data looks like. We'll see how many missing value it has, and if has yeah, how do that process if it has any missing value. We'll see that also. Then we are going to normalize the data for LSTM. LSTM works better with the data is scaled between 0 to 1, so we can use scaling technique here. We have been using scaling technique for we have used it for like two or more than, yeah, four or five problems, and we have understood in depth what and how they work. So mostly we have used two type of scaling, a one counter scaling and second is standard scaling. This standard scaling, now this min max scaling is a little different, so we are going to understand why we are using it and how does it work and how difference what is the difference between this standard scaling and min max scaling. So it says that we will normalize the consumption using min max scaling. So we'll get the consumption, this is going to be our feature. Okay, and then we'll create the object of our scaler, and then we are going to transform, and we will see the scale data. Okay, now we will do what? LSTM expects the data in sequences, meaning that for each time step, the model will use previous time step to predict the next value. Okay, we will create sliding window of the time steps. So we will be using a sliding window technique to predict the next value based on the previous steps. For example, if you want to use the previous 30 days to predict the next day, you need to convert the data into sequence of 30 days. Okay, so for that we will import numpy and create a function to create sequence, and here we'll get the data and the time steps is going to be like, I guess, 30 days. Yes, the window size, like how for next 30 days if we want to predict, so we want data for the next previous 30 days, as in the next 30 days. So the window size is going to be 30 days. So we'll have sequences, target, and we'll range from the data to those steps. And we are going to do this thing that we are going to understand data. Then we are going to create sequences, X and Y's. And once done, we are going to do what? Split the data into training and validations data sets. And training is going to be of 80%, and the we will perform validation on the rest 20%. We will do that using this. Okay, we will do that using this. Now we are going to, this is a little different from what we have been doing with our previous problems. Next, we will build the LSTM model using Keras and TensorFlow. Don't worry about complex deep learning concepts yet. We will focus on just building. Yes, so today we are just going to focus on building the model. We'll see how it looks like, and maybe in future we are going to understand in depth what and how they work. So we are going to create an LSTM model. We are going to add LSTM layer, and then add another the output layer. We are going to compile it, and then we are going to train it. Okay, and then we are going to evaluate. I guess we will be evaluating based on this technique called. So we will inverse it. So I do not understand why we are doing it, but yeah, we'll ask ChatGPT for that. So okay, so yeah, let's start. Uh, Let me move this again here because I started the video again. So yeah, uh, so thanks. It makes sense. However, I still have found many places, pieces of code, lines of codes that did not make sense to me. Like, like what? Like, how do we handle missing? Like, let's put it in bullet lines. Values. Are we going to drop them? Then we will see what we are going to the how and why of create functions. Each line. Then uh, why the is split technique is different today from normal uh, classic machine learning problem model. Then we need to understand, can you just touch and explain the parameters of LSTM model compile and model fit, and why are we doing scalar doing inverse transform for evaluation? So this is going to help us understand that. So yes, we have asked all the questions. Okay, let's understand each question. So it says, great question. Let me explain each part in detail to clarify the concept. In time series, missing values can occur for various reasons, and how to handle them depends on the problem at hand. There are common strategies. We drop them, and if we do not drop them, we do what? Interpolate missing values. A more common, we have used this technique before, but we have not used this technique before. So what it is? The more common technique for time series is interpolation, which estimates missing value based on the previous data point. This is better suited for time series because it keeps the continuity. Yes, it keeps the continuity. We are not going to, let's say, if we have missing values of consecutive 20 days, dropping them will leave the continuity. So I guess for our today's problem, interpolate missing values is going to be better because it is going to predict the value for the missing row or the missing value based on the previous values, previous data points, or the neighboring data points. In the time series, continuity is essential. If you drop data, you lose potentially important temporal information. Interpolation helps you fill in those gaps smoothly without losing too much data. So we are going to use interpolation. Next, understanding the create sequence function. So what? Let's do what? Let's start with coding. and I'm going to get the database dataset from the cable only. So I'll say we want data electricity consumption. So let's go back here. Elec- Electricity consumption data set for time series forecasting, and we can get that from here. Energy consumption time series forecasting. It looks like this. Say transaction date, transaction time, and consumption. Consumption. Let's go here. With where can I find the dataset? Okay, we have too many CSS. I know which one I want. Contains hourly and music and data, certain data for multiple cities. You can choose one of the sites and forecast electricity consumption. This is ideal for predicting future consumption based on the past hourly data. Let's look at this. I guess this makes sense. It has date and the consumption. Date and the consumption. And for how many? Like, files it has. AEP hour Dighton. So I guess these are the file names. So I'll go with AEP hourly consumption. I don't know what city or country it is, but yeah. So maybe I'll go with this. So let's do what? Let's go to our PyCharm. Create a new Python file, called it as t26.py. Add it to our Git repository and specify what the problem is. Problem is this data set. What is the data set that we are going ahead with? We'll be going with this data set, AEP hourly. Here we could, I guess, see that AEP. So if we are going to go, we are going to import pandas SPE, and then step number one, we will load the data, and we will do what? Data is going to be loaded from panda read CSV, and for that first we have to move the data set. So we'll have to move the dataset from, let's go to the downloads folder, and let's go back here. And here I'm going to move firstly out of this folder so that it becomes easier for me to move. So I'll go move downloads AEP Hourly data sets. And this is, let's go what, clear the terminal, go and check, we do see the data set, and load AEP Hourly data set, and then print the data set dot info, and then print the data set dot head to see few rows, and do what, run this to see how this data set looks like, q26.p1, and this is how the data set looks like. And so I'll go what, I'll say thanks, i i i I decided to use hourly energy consumption from Kaggle, and it's AEP hourly data set, and here how it looks. Yes, so it says congratulations, great that we are using this. So let's understand each step. So what we are going to do, we load the data, convert the data in column to date time object, because why we have done this in previous problems as well, because machine learning understands date time, then it is becomes easier to convert it into numeric time. And then we are going to set this date time as index because it becomes easier for plotting and understanding. And then we are going to check for the null values, and if there is any null value we are going to use interpolate technique, which is to find the missing value based on the past values and uh, convert them, and even after that if there is any missing values we are going to drop them so that we do not have missing values. So let's do, come back to our code and do the steps. So what we are going to do, we are going to sorry, yes, we are going to convert the date time column to date time object. Convert the date time column to date time object. So what we are going to do, data, and it is, which is the column, this is the pd to date time, this data, this column. Once done, set the day as index, data dot set index date time in place, yes, true. Once done, we are going to check for missing values. So the print data is null, and what we are going to do, we are going to sum it up and see the data missing values and count. So the missing value count is, let me go and hide it and run it again. So the missing value count is, so the date time has become the index. Now we are left with only one column, right? So if I do what, if I move it here, and if I move it here, you should see now I have two columns. Here it is saying that I have only one column. which is this AEP MW. Because why it is not considering the other column, because it is treating that column as the index. That is why we saw only one column. Now we are going to put it back here and comment it and give one space. So yes, we do not have any missing value. We do not need it. If we would have needed, if there would have been any missing values, how would we handle it? Interpolate. First, use interpolation to predict values from past neighbor data points. From neighbor data points. Okay, that's it. So how would we do? How would have been do? How we would have done that? Dot interpolate and drop the missing if left any. So we would have done that. And drop data is equals to data. Drop drop any. But we do not have any missing values. So we'll do what? We'll print the data head again to see how the data looks. Yeah, good. So what we'll do, the step number one is completed, step number two is completed, step number two is this, handle missing value if any. So okay, so now we are on the step number three. So step number three says it is crucial to normalize the AEPM underscore NW values to a range between 0 to 1. This helps the LSTM model coverage faster and perform better. So we are going to use this mix max scalar. Now I want to ask this mix max scalar here to uh, why are we using mix max scalar and how different it is from standard scalar, because we have used standard scalar or scaling technique previously and we know how it works. I am curious to know why we are using a different scaling technique here. So it says let's explore why are we using the max scalar and how it differs from the standard scalar. These are both feature scaling techniques commonly used in machine learning and deep learning to normalize the data, which helps model coverage faster and perform better. However, they work in slightly different ways and their use depends on the nature of the problem. In our case, LSTM, long short-term memory models, and the time series forecasting, it is common to use min-max scale because LSTMs are sensitive to the scale of the input. Okay, if the data has very large or very small values, it can slow down the learning process and lead to poor conversion. Here's why min-max scaler is useful. So it scales the data to a fixed range, usually between 0 to 1. This ensures that all features are in the same range, making it easier for the model to learn. Okay. The scaling technique is particularly useful in the time series forecasting where the values may not follow normal distribution but are bound. And how it works, X is the original value, how it calculates. And for example, this in your case electricity consumption may vary between 1000 and 2000. Now if we go and see, the value varies, like it comes in like 10, 14,000, 14,000, 15,000, 16,000. Here it is 18,000. So yes, R value varies from 10,000 to 20,000 megawatt. Now, scaling the values from 0 to 1 helps the model handle the variation more effectively. Okay, so we are using it because it converts scales the data between 0 to 1. Now, how did it do? The formula is that the x is the norm origin value, x min and x max are the maximum minimum values in the data. X scaled is calculated as x minus minimum divided by x max minus x min. So it comes between the this range. Okay. This means that after scaling, the smallest value in the data will become 0 and the largest value becomes 1. Okay. Why? Because this will largest will be max minus max will be 0. Max minus means, let's say our value is 2000 minus x min is 10,000. So 2000 and 10,000 is 1000. And the value of the maximum is 20,000. Minimum is 1000. So the denominator and numerator are same, so it will be 0, sorry 1. And in case of max minimum, this term will become 0. So yes, all the values will be scaled from 0 to 1. This is, I guess, easier to calculate. Standard scalar is calculated on the basis of standard deviation and mean, and here min max scalar is calculated on the basis of minimum value and maximum value. um, Now we need to understand, so we understood how it works and how it calculates these scaled values for each uh, data point. Now we need to know how it is different from standard scalar. So it says that standard scalar transforms the data by centering it around zero and scaling it based on its standard deviation. Yes, that's what I have told you. The results are based having a mean of zero and standard deviation of one. It is used when the data follows a normal distribution. Okay, so our data does not follow a normal distribution. Our data can vary a lot. So yes, the formula is like the scale value. It will be calculated like x is going to the original value minus the mean divided by the standard deviation. Now, min-max scalar scales the data between a fixed range without centering it around a specific mean. It preserves the shape of the original distribution without but compresses the range of the okay. So it preserves the shape of the original distribution but compresses the range of the value. It is better choice when you know that your data are bound has bounded limit. Like electricity consumption, we have a bounded limit. So in that case, the min-max scalar is optimal to use. That is, or when the data does not follow a normal distribution. So when to use min-max scalar? When the data has specific bounds, like our electricity consumption. You don't assume the data follows a normal distribution, Gaussian distribution, and when we want to preserve the relationship. And we use standard scaling technique when we data follows a normal distribution and we want to when we want the data to have a mean of zero and standard deviation of one. And it is often used for linear models like logistic SVM because they may benefit from data being centered around zero. Yes. So when we want to keep the relationship, we use min-max scalar. We have specific bounds, then we use min-max scalar. Otherwise, when we want to follow normal distribution, when we want to have a data, the data to have a mean of zero and standard deviation of one. When we want a data to be centered around zero for like logistic regressions or other linear models, we use standard scaling. Yes. So example of min-max scalar applies this feature scale 0 to 1 scale. After scaling, all the values of the scale will be 0 or 1 and making it easier for LSTM model to process the information. Yes, so let's go what we've understood what this LSM is going to do and how it is going to do. So it is going to range all the values from 0 to 1. And what would be the formula? We saw the formula as well. So let's come back and implement it. So import the libraries. So libraries are going to be from sklearn preprocessing import min max scalar, and here scalar, it is going to be min max scalar. We need to find the feature range will be from 0 to 1. Okay, and then we are going to put x, sorry, data scale, and it is going to be scalar fit transform, correct, and fit transform on data, which value, this AEP megawatt value, and then we are going to simply see how the data, the scale data looks like, and clear it, rerun it, and we have error. Okay, here we need to pass it like this. So it's all we are this. It happens like whenever we are doing what we are trying to do what. So what I have understood till now is that machine learning expects multiple features. So when we are giving single feature, we need to pass it as multiple feature. That's why it was giving the error. It says that it has no head attribute. Let's say print it, and this is the value coming 0 to 1. The value is coming like this. I'll go and yes. Now we'll do what? No, check the first 5 rows of the scale data, and I have checked first and at 5. So, these are the first 5 rows, right? So check first 5 rows of scale data. Okay. Now in the step 3, we did not mention what we want to do. Step 3, we are normalize the data using min-max scalar. Now we'll do what? Remove extra space and go to step number 4, which is create sequences for LSTM model. Create sequences for LSTM model. Okay, so we'll do what? We'll use sliding window. We saw, I guess, we saw earlier as well, right? That for LSTM, what we need to do? Yeah, we saw LSTM. Yes, did we see? Did we see? We did ask, right? What LSTM is like? We saw, yes, we saw what LSTM looks like. We all saw, right? So let's come back here. I forgot where this that was. So we'll use sliding window LSTM model. It is useful. Why? Because it uses a window to predict the next data point. To make the prediction from the past data points. It uses those past data points to make the prediction. And how many data points it is going to use? It is going to use from this window that we specify. So, for example, we specify for 60 hours. To predict the next hour, we need a window of 60 hours. We need the data for previous 60 hours to predict the next hour of electricity consumption. So the create sequence function will help us transform the data into the format that is needed or understood by the LSTM model. So yes, how it will it do? We will create a list of sequences attached. A range will go from length of data, how many data, whatever the data we have, minus the timestamps, and we will add that to sequences and target. Zero. Yes, this is how it looks. I'll say, can you please describe this? Please describe this. It is that let's break down this code step by step, as it is an essential part of preparing data for an LSTM model and a time series forecasting. So it says, yes, let's understand. We need to create sequences. This function is used to convert the time series data into input-output pairs that can be fed into the LSTM model. In time series forecasting, we use a sequence of previous time steps, which is we have specified 60 hours of data to predict the next time step, which is the next hour's value. This function helps create these sequences of data. So here we specify two arguments. First is the entire data. This is going to be the entire time series data. In this case, it is going to be a scaled normalized data. Here time steps. Here time step we will go with 60 seconds time step. We'll go with what? 60 seconds. We'll go back and we'll see what. Here I see time steps are going to be 60. Yes, that's what I'm defining. So the window size here is going to be 60. On the basis of that, calculate the next value, next hour value for consumption. Now, initializing list of sequences. Yes, this list will store the input sequences, that is the previous 60 hours of electricity consumption. List will store the corresponding target values. That we have to calculate the electricity consumption value for our hour that comes after the sequence. So let's do what step by step. Do this. We have to create uh, a function called create sequences. Here we say data, and the next is time step. The data is going to be a scale data, and the time step is for how long we want to, the window size, and that is, and this is our going to be, and this is data is going to be this, okay, and time step is for this, okay. Now we'll do what? We'll do what? Create to list sequences and target. This will store our list of input sequences, that is 60 hours in our case, and this will store the list of the next hour that we want to calculate. Loop through the data. Now we want to understand what it is doing. The loop iterates over the data set, starting at the index I and going up to the length of the data minus time set. Please ensure that we do not go out of the bound when creating sequences. For example, let's say our data is 40,000 minus 6c. So it is going to be the data has 10,000 steps. Time steps is 60. The loop will iterate from 0 to 9940, so that each sequence ours has a corresponding target. Okay, makes sense. So for each sequence, the window size is 60 hours, right? So for each sequence hours, so that each sequence of 60 hours has a corresponding target. Yes, let's see what it means. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A window size is 2. So my window size is 2. Let's say 1, 2. It will calculate 2. Then I'll calculate for third. Predict for third. Then I'll move to 3. Then I move to 3, 4. And then I'll move to 4, 5. And then I'll go 5, 6. And then I'll go 6, 7. And then I'll go 7, 8. Then I'll go 8, 9. 10 minus 2 is 10 minus 2 is what? 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8. So 1 to 8. So 9 minus 8 is 8. So we'll go till 8 only. 9. So this is going to be our I. So this is going to be our I. No. This will be our I for the next data sequence. Right? So the next data sequence is going to be, we need to stop here. So 10 minus 2 is, so let's say we need to stop here. Right? Because we want to evaluate. So this data set will be used for this one, window size. Okay, makes sense. Little bit, but yeah, maybe I'll come back in the future. So now what we are doing for each iteration of loop, the code iterates, it takes a slice of the data set starting with the index of I and go to what time series. For example, here it will go from I is 0, I is suppose 0, and data set is 2, so it will go 1, sorry, 0, 2. I mean, it will slice 2. Then it will go from 2 to this. Then it will go I is 3, 3 to this. Then it will go I is 8. It will go this to this. Right? So this is creating a sequence. So it will go from I and I plus time steps. Next value is target, and it is we need to calculate the target is going to be I. So for 1 to the target is 3, so I is 1, sorry, I is 1 plus 2, the window size is 2, 1 plus 2 is 3, so the target is next one, right? So that is why we are getting that way. So we'll do what for I in range of length of data minus time steps, and we'll do what append sequences dot append uh, data from I to I, sorry, from I to I plus time steps, from I to I plus time steps. Okay, and we need to update the target is going to be append data I plus time steps. And yes, that's what you want. Now we will simply return these sequences. We will return these sequences and we will do what? After we let the list sequences and targets are converted to NumPy arrays. NumPy and why we are using, because NumPy arrays are used because they are the format expected by TensorFlow or Keras when feeding the data into LS. Okay. So LSTM model expects them to be a NumPy array, so we are going to return them as NumPy array. So let's import that first. Import NumPy as empty, and I've got a mixture different space, and we will return as NumPy.array sequences, and then we will put NumPy.array target. Is this what it is? So for example, the data is like that times 1. So for time series time steps 3, size of window is 3. This is going to be the target and this is the window. Exactly, that's what we saw. Right. So the sequence is going to be 10, 20, 30. The target is 40, 20, 30, 40. Target is this, and yes. So yes, let's go back and create the sequence because that's being expected by the what? The LSTM model. So we have written the this. Now we are going to do what? Time steps are going to be 60 and creates premises, that is create sequences. So sequence is X. Oh, that is the target value. Nice. We are creating this in that like create sequences and we are going to pass the scale data that we have scaled and the time step which is 60 seconds. And we are going to print x dot shape y dot shape. Let's say we are doing what? Check the shape of sequences. Let's go what? Run the model again and see run the script again and see how it looks. So we have 1 2 1 2 1 3 61 and it is 1 2 so it has 1 2 1 2 1 3 column and 60 in each of that row 60 items and it has 1 2 1 2 1 2 entries. So yes, so this is how it looks. Now we go what output. Now we go what split the data into training and test sets. And we will do what? We will split the data into training and test sets. How the data is in the form of numpy arrays. We will not be applying. It is not a data frame, so now it makes sense that we are going a little different. So what we do split the data. Step number 5: split the data into training and validation data sets. Okay, so with train size is going to be length of x multiplied by 0.8 80%, and we'll do what? We will do what? First printing train size, and we will comment that we do not want to see that anymore. I want to hide something else as well. This also. Let's clear it and run it again. And train size is this. So out of 80% is going to be these many. So now we need to convert it into it integer. So train size is this. So what we are going to do? X train and X validation is going to be X from start to stop at uh, train size, and X the validation is going to be train size to and at wherever it ends we can find. Then we will do what? Y train to Y validation. Y we want from train size. Y from train size to the end of the array. Now we will check the shape of the train and test. Check the shape of train and validation data set. Print x train dot shape x dot validation dot shape, and we will do same with y train y validation. Run it, and this is how it looks. This is 96970 60 60 the time series set, and this is the rest similar for the y, right? Now looks good, and I will go and comment it. Now we will build and train the LSTM model. Now it is we'll do what? Step number, which step is 6 is build and train the LSTM model. So we'll do what? Come back here. Use TensorFlow and Keras. We'll build the model, LSTM model. Add LSTM layers with these many data points. A simple LSTM network with 50 units is used, and it is shared on epoch, 20 epochs. So I'll ask this the 50 units return. We'll just understand what this is. So let's do what? Import the libraries first. So I'll go back here, import TensorFlow LSTM, and TensorFlow.keras.models from TensorFlow.keras.models. Import what? Sequential from TensorFlow.keras.layers. Import LSTM dense. I want to see, I am curious how does it look like. If I see LSTM, I will Google it, and this is how it looks like. So here you see it is a neural network in deep learning. We pass in the input. Here it has multiple layers: layer 1, layer 2, layer 3 layer, and the output layer, a single output. Now what happens? We pass in some data points in numbers, then they work on it and they create a layer, and from this the second layer is created. From this the third layer is created. As an evaluation happens, and they minimize and then create the second layer, minimize and then create the third layer, and then thus they create the output layer. It is a RNN, recurrent neural network, that can contain long-term dependencies and sequential data. Right? So yes, now let's do what? Let's ask. Thanks. Can you explain this now? Yes, let's go and understand how the LSTM model is created and compiled and trained. This model process is fundamental in time series forecasting using deep learning models like LSTM, long short-term memory networks. So we are creating a sequential model. This model, the instance of the sequential model, LSTM model. So this function initializes a sequential model, which means that the model consists of linear stacks of layers, where each layer has exactly one input and one output. Okay, and we are stacking layers one after the another in order we define. This line adds the main LSTM layer to the model, and let's break it down. This LSTM 50, this is an LSTM layer with 50 units, neurons. Then 50, the number 50 refers to the dimensionality of the output space of the LSTM layer. In other words, this LSTM layer will learn 50 features or patterns from the input sequence. Okay. Why 50 units. Choosing a number of units in a hyperparameter that you can adjust. Okay, is a hyperparameter that we can adjust. More units allows the model to learn more complex patterns, which they can also lead to overfitting or longer training time. A typical starting point for the times. So I sense that this is something we are defining with how many neural networks we want for each layer, and we are going with 50 so that we do not overfit or do not have the longer time of waiting time for training. Then return sequences. These parameters control whether the LSTM layer return the full sequence of output or just the output for the last time step. Okay, so it says whether it should return the output for this, or the last one. So we say no. We only want the output of the last time. So we only want the output of the last time step because we are predicting a single value. Yes, so we are saying that we only want this output. We don't want the entire output of each layer. So that's why we are saying false. And then here's the input shape. It defines the shape of the input data. The shape one, this is the total number of time steps in each sequence, that is 60. So this is the shape of our, the 60, the first row, the row size. And one is the number of features in each step. How many features we in each step we want? You only have one feature, that is electricity and yes. So here it specify how many features we have. We have only one feature, which is electricity consumption. So the input shape to this LSTM model is going to be 60 is to 1. 60 is to 1. The number of timestamps in each, and then the number of features. Then we add a dense layer. Let's do what? Let's do step by step. Create the model. We have understood we are creating a sequential model with this model sequential. Then we do what? Add add an LSTM layer with 50 units. Add an LSTM layer with 50 units. So what we are going to do, model dot add LSTM layer. Here we define how many input units we want, 50, and we want to return the output from each layer. Return sequences, no, false. And the shape of the input is going to be input shape. Input shape is going to be x train dot shape of one. The row, the first row, which is 60 in our case. And how many features you know? 100. Then we say adding a dense layer. Now we are adding the layer. So what layer it is? These are the dense layers. We are adding those layers. So the dense layer is a fully connected layer. It is used to produce the output of the model. In this case, we want to predict a single value. So we specify 1 unit of dense layer. Why a dense layer? After LSTM layer learns the temporal pattern in the data, we need to map the learned representation to the actual prediction. Okay, the dense layer takes the 50 outputs from the LSTM layer and combines them into a single predicted value. Okay, so it takes 50 LSTM layer from the input layer, output layer, and then combines it into a single value. And I will do what? I do not understand that much, but I do. I add a dense layer to output a single value. And a dense layer to output a single value. Maybe we need to do a full-fledged challenge on machine learning. Before that, we need to see and read some topics, clear some topics like we did for the basic linear models. And now we'll compile the model. Now we'll compile the model doing what? The optimizing is the algorithm that we use to minimize loss function. Loss as in the minimum loss that we can have. We are using this, and the loss function. How are we going to calculate the loss function? We are going to calculate the loss function using mean squared error. So choose the algorithm to minimize the loss function, and how are we calculating the loss function using this? So compile the model. Compile the model. So we are doing what? Model dot compile. Here we are specifying optimizer is going to be what? Adam and adaptive moment estimation, and the loss function is going to be calculated using mean square error. Done. Now we'll go back and then we will train the data. We'll do what? Train the model. Train the model, and it is going to be history. And it says history, so we are going to fit. We are not calling it as predict. Sorry, we are just storing things in the history. We are passing x string x y train, I guess. And here, let's understand this. X train, y train are the course. So this fit function is where actual training happens. The model will go through the training data multiple times. That is, how many times you want the model to go through the loops. That is 20 times. And with each loop, yes, this specifies the epochs, that the number of times the model will go through the entire training data set. Training for more epochs can help the model learn better, but too many epochs might lead to overfitting. Makes sense. Unless to yeah, and the batch size refers to the number of samples the model processes before updating its internal parameters like weights. With a batch size of 32, model will compute the loss of 32 samples, adjust its weights, and then move on to the next batch. Okay. Larger batch size may lead to faster training, but smaller batch size often result in better generalization. It is like we have 1,000 data points. So in 32 batch size, it is doing first training, then 32 next, then 32 next. This is how it is moving. And how many times it is going to cover this loop? 20 times. We'll do that with epochs. And validation data is this allows you to evaluate so in how it is improving, how why it is going to the loop iterating a second time, because to make sure it is getting better, so we need some validation data as well. So this allows to evaluate the model's performance on unseen data after each epoch. By comparing the performance of the training and test data, you can monitor the overfitting and see how the model generalizes. So we need to specify the validation data as well. So we'll do what? We specified the training, the data we want to train on. Okay. Then we how many iterations we want to do? 20. And each iteration, the batch size is going to be 30. And the validation data is going to be X validation by validation. Now let's go back to our step. So yes, we have done it. Now let's go to step number 7, which is to evaluate the model. Step 7 is evaluate the model. So once we have so a model is done, we need to evaluate it. So first make prediction. So we are doing what? Prediction and predictions, yes. And we are doing what? Model dot predict on X validation. Okay. Inverse the scaling of prediction and actual. So why I am curious why are we doing that? Why we did explain? We doing this. Please explain. Actually, what I'll copy paste everything here. mention it here. Let me see this. Yes, here we are simply predicting our validation data since the model has already learned the patterns in the training data. So why inverse transform? During processing, we applied min-max scalar to normalize the data between 0 to 1. This was necessary because LSTM model performed better with the data when they are scaled. When it is scaled to a smaller range. However, after making prediction, we need to reverse this normalization. Okay. To bring the predicted values back to the original scale of so we need to so this predictions has been made in the normalized state. We need to bring this prediction back to the original values, the original electricity consumption rate. That is why we are doing this inverse transform. It transforms the predicted value from the scale 0 1 back to the original value, which represents the real electricity consumption. So what we are going to do, we are going to transform the predict. So we are going to do predictions, inverse transform, inverse transform predictions, and we will be able to see it in the original form, the original like 10,000 to 20,000 range. Then we would do same thing on similar to prediction. We need to see the Y test. Did you see that we have evaluated this Y test, this Y validation on the scale data? That first we created the sequences and sequences we created on the scale normalizer. So that also we need to convert it. So we'll do what? Inverse that also. So Y validation uh, scale. I said original. Why scale? So we'll do what? Scalar dot. Okay, from the scalar inverse transformation Y validation dot reshape from -1 to here this reshapes the valid array to have one column and specify number of rows, one column and specify rows. So -1 lets the empty automatically figure out the number of rows. You would have like unspecified rows, and we will have one column. And this is going to be the original value. So we are going to reward visualize. Visualize the visualization. We are going to reward visualization. So we'll plot a graph, import the library. We will do what? We need to define the build the figure. Here we need to specify the size of the figure. It is going to be 10:7. Then we will build the plot, and we have already specified the index. The index is going to be the date time, if you remember from here. Yes. So from date time on x-axis, we want to build the plot against the original values, and it is going to be the label actual consumption. Label is going to be actual consumption. And then we will build the plot of predictions made against the index, which is data. It is predicted consumption, and we'll do what? At electricity consumption forecasting. plot dot x. Label is going to be time. Plot dot y label is going to be consum- consumption in what megawatt, and then the title of the this plot is going to be what electricity consumption forecasting, and we'll need to see what each plot represents, as in what each line represents. So we'll do what? Mention it using legend, and then we'll show it. Now we are going to run it. We need to split it in. Yes, let's run it. Expected time is 23 seconds. Oh, this is for one iteration, and it is going to do that iteration of 20 times. And here we see the batch size. See, the batch size is increasing. Here we also see the loss for each batch size. So I guess we might have to wait a little. Maybe to perform 20 iterations. I'm so sorry, my cat stopped the video. So it will go back. This is how the model has after training looks like. It took like 6 minutes to, I don't know where the cat stopped the video. So it took more than 6 minutes to train the model, and I did take the screenshot. So the screenshot looks like, let's go back, and looks like this. So this is how it is looking. Uh, we see that the actual value and the the predicted values are overlapping, so the model is predicting the values very well. Uh, Let me do what? Let me ask the ChatGPT only. I'll say for me, I think the model is looking really solid. But yes, let's say uh, I'll move it here. Here, how the model is trained. The model here, how the output is looking. How well do you think the model has performed? Again, uh, yes, see, the model has performed quite well because since both the lines are overlapping. Yes, so yes, we can say the model is performing really well. Let's go and commit the code. Day 26, sorry, and commit the code, add code for day 26. Push to main branch. I'll go here and see if the code is visible. And yes, we can see the code. So yes, I don't know how and where the cat stopped the video. So I'll go and check out. But yeah, this is how the model is looking. Will come and now I'll go and upload this video on YouTube, and you can also see the textual format of what we did today on this tech journal. So yes, let's stop the video and meet tomorrow for our 20 27 call.